So what I wanted to do was I wanted to spend some time to go through and talk about the Smith-Waterman, not Smith-Waterman, the Needleman-Wunsch algorithm, because I think that this is actually quite an important algorithm to cover. It's the first algorithm of its kind for bioinformatics like that. Then there's another one that followed called the Smith-Waterman. And that one is actually very, very similar to this. And so I'm thinking that if you can understand this, then if you understand like how this particular algorithm works, then you'll be able to figure out the other one in no time at all. But I just wanted to take some time actually today just to show you how these algorithms work, because I mean there is a certain there's a certain kind of magic, I guess, in these things, if you can call it a magic. I do find that there's something actually quite exciting about them. But anyway, we're going to we'll talk about that. Some of these slides you may have seen before because I used them when I described the other stuff on Monday, or this algorithm on Monday. But also we are going to talk about the influenza virus. That's the part 2 of these things, and we'll see how much of that we can get done today. So we've got a lot of things planned today, and so I hope that we get it done. But otherwise, if we don't, then it'll just spill over, and we'll finish it on Monday. Okay, so let's go ahead and get started. So this is the first slide. So this is the Needleman-Wunsch algorithm, and as you remember, we use this for global alignment. This was built into applications like your Clustal, and we talked about this in BioPython. And by the way, I do hope that you were able to get your BioPython code working from Wednesday. I hope you were able to look at your code, and if you made any mistakes, then I hope that you were able to find those errors by comparing your work with the code that I gave you. And so that should be okay. But also we had that activity which is due like now. So get that done if you haven't done that already. Anyway, so global alignment, you should basically determine how one big sequence is related to another big sequence. You're really comparing two giant sequences to each other. And it was developed, the reason why they call it the Needleman-Wunsch algorithm is because it came from someone called Needleman, who worked with someone called Wunsch. And the nice thing about this is that, I mean, look at this algorithm. It came from the 1970s. And so the nice thing about computer science is that when you develop an algorithm, if you have a solution, if it's a solution for something, then you can use that algorithm for that solution. But if you can take another problem and bend it into like the original type of problem that the original algorithm was designed for, then now you have a solution for two things, the original problem and the new problem. And so this is an algorithm which was designed to compare not necessarily DNA sequences, but other kinds of sequences. And you have this thing. Good morning. And so anyway, you have this really clever algorithm that has been now used in bioinformatics. It was borrowed for bioinformatics. And so as you go through the history of bioinformatics, you'll see that some of these algorithms have been kind of reapplied to other areas. For instance, this algorithm was also used to compare proteins, which is another new thing. I mean, new compared to the 1970s when this algorithm came out. Anyway, but before we go any further here, we need to talk about some terms, and I briefly went over these on Wednesday, but I didn't actually give you much information about like what they mean, and so I thought that we would do that now. But basically, though, we're going to be breaking up this alignment problem into like sub-problems. That means that for every single comparison, when you're comparing one base with another base, you're going to be looking at making basically 3 different calculations. And so that's what I mean by a subproblem. There's like 3 small calculations to be made for each comparison that you make. And I'll show you what I mean in just a moment here. But just think of this in terms of like breaking down this giant comparison problem into smaller problems. Now, when you're creating solutions here, you're keeping a score of your solutions as you go. And so those solutions that score the highest, in other words, the scores that you saw when you used BioPython, those scores which are the highest are the best solutions. That's how the algorithm works. You have a way of kind of determining the best fit is for your alignment according to the highest score. And so we're going to spend some time to see how that score is calculated. Next, we have what's called a match, and that's if the 2 bases that you're looking at are actually equivalent, if they're the same base. And obviously, the opposite of that is a mismatch, where if the base on one sequence does not equal the base on the other sequence. So for instance, you can see that in the sequences below, I have my sequence on top begins with an AG, Well, the AG, the A and the A from the top sequence and the T on the bottom, that's a mismatch. And so that's like, it's not the same. But a match would be where I have at the same place. If I move on down maybe 5 places, I find there's a T on the top and then there's a T on the bottom. That's a match. Now, a gap is where, if you look down at the bottom sequences here, where you have that dash, that hyphen, that is a gap, where, for instance, the sequences are not the same, and it could be that dissimilarity could be explained by some kind of an insertion or a deletion of a base, like something has been removed or something has been added to kind of put everything out of register with each other. So you can see those dashes are what they call the gaps. So when you actually create your pairwise alignment, as they call this, the global pairwise alignment, or the algorithm that we know to be the Needleman-Wunsch, you're basically creating this giant grid that looks like this. It's like a giant, I guess in math they'd call it a Latin square. But for each of these numbers you see in this Latin square, there are 3 calculations that have to be done. And when you do the calculation, you're going to be doing 3 different calculations, and you leave an arrow depending on where the numbers came from for your calculation, which yields the highest answer. So I know that just sounds like a bunch of gibberish, like what is he talking about? Well, what this means is you're creating kind of a breadcrumb trail, if you will, throughout this Latin square, and you can follow these arrows from where you end back to where you begin, and that will tell you what the alignment looks like. So let's go ahead and let's see an example here. So how do I begin this? So to begin this, you have to align your, this is what they call dynamic programming. It's not efficient programming, but it's because you have all these different calculations to make. And what you're doing is you have to make this giant kind of Latin square where you put one sequence on the horizontal and the other sequence on the vertical. And you can see now that, hopefully you can see now, that if there are 3 different calculations to be made for each comparison of the bases, like for instance, when you're finding out these numbers, the calculations actually get, or the amount of computational work actually builds up very, very quickly. And we'll see that in a moment. So basically, to start out with, I'm looking at these instructions here. You create an n by n matrix. Your n is going to be the size of your first sequence. Your m, as in Marvin, Nicholas by Marvin, is going to be the sizes of your 2 different sequences. You put a 0 in the upper left corner. That's really kind of something of a placeholder. You never, but it needs to be there because, but you'll see in a second. It helps with the first calculation. Fill in the first row and column with gap penalty multiples. You're going to have to be told how to score this thing. And so, for instance, the score is going to be a gap penalty of -1. Now, what that means is that if you have one of your calculations you have to make is going to be accounting for gaps which may appear. And so you have to know that you're supposed to subtract 1 point if you find gaps. After all, how this thing works is that the more bases that you get correct, then the higher the score gets. It's like in a game of basketball. The more baskets you hit, or the more times you get the basket through the hoop, the more points you get. And so this is the same way. The more bases you have lining up, the higher the score. And so if you don't have those things lining up, if those bases are not, then you have this penalty of -1, which is something you have to use for your calculations. And then you have to fill in the matrix with max values of 3 possible moves. I'll just call this the vertical move. And basically what that is you're making a calculation from the vertical, from the vertical cell relative to where you are. You have to make a calculation from the horizontal cell relative to where you are. And then you have to make a calculation from the diagonal cell relative to where you are. Now you'll see how these scores all come together. But remember though that this is actually a very important piece here, and that is that the gap penalty score, which is right here, is only used when you're working with vertical, like up and down, and horizontal, left and right. The diagonal move, it has nothing to do with that gap penalty score. In fact, you're using a different score entirely, which is the mismatch. But you can see what's going on here. Then once you finish this, you have to backtrack on your arrows and you can see what's going on. But let me just show you, this is what the algorithm looks like formally. So the 3 calculations are written at the very, very top here where you have this, hopefully you can, I can't select anything anymore. I can't select anything. My mouse isn't working, but you have 3 different calculations to make, but don't worry about that. Let's just look at how this thing actually plays out. So remember, though, that you have to put out your 0 in the top corner, which is right here, and then you have to put in you basically have these numbers here. These are all multiples of your gap score right here. And they start from -1 because minus 1 is your gap penalty. That's basically what happens if you lose points because you have a gap. You do that, you put those numbers here, and then you also have those same numbers, down here. We have -1, -2, and -3. So we haven't done any calculations just yet. We're just putting out numbers, getting everything set up. The calculations that we have to that we actually do begin right here, where you're looking at, for instance, you start with the first. You guys hopefully can all see the red. But you have your T and your A. So first of all, I have to calculate how similar is T to A according to this algorithm. And so what I do is I say to myself, okay, well, T and A and T are not the same. So we would call that a mismatch. And so I need to know now that I'm using this mismatch score here. So over here, I have to make I'm going to make my calculations based upon 3 different things here. So first of all, I have my upper box, which is, I call my upper box, which is this up here, which is -1, and this is the calculation up here, -1 is equal to -2. Well, what is that -1 there? Well, that number, let me just give you an idea about how to read this thing here. That's my gap. Notice these 2 arrows, either up and down, or left and right, to tell you that you're supposed to use this gap value only when you're looking at the column or the cell directly above you or the cell directly to your left. Whereas if you're working with a match and mismatch, this stuff is only used when you're working with the diagonal, the catty corner cell to where you are, the diagonal cell. That's just how I mean, if you have a better way of remembering this, then please use that. But how I do this is I just remember that the gap, you use this you have this you're either using that, or use that score with the above and the left score, or the left cell, and use the match and mismatch values for the diagonal. So that's what these arrows mean. Anyway, but I have to make 3 different calculations per cell. And so the first one is the upper box, where I'm looking at where I am right now, which is, I'll just go back over here. I'm looking at right above me where I have -1. -1. So I say, okay, -1, and then I have to kind of just take my -1, and I have to subtract another 1 from it because it's the gap. I have to calculate it. You just have to calculate this gap. So -1, -1, and that's where this value comes from here. That's my upper box. Now, next I have I have to do my side box, which is I'm looking left where I am right now. And so I have this value of -1 over here. And again, I have to subtract my gap score. So in other words, I get the same value for calculating above me as I do on my side. -2, -2. And then I have to take on the diagonal. So what is the diagonal score that I have? Well, that's the 0 that I put down. And so that's 0. Now, here's the thing, that because A does not equal T, then that is a mismatch. And so I take this value 0, and I add it on to whatever my diagonal score was, or subtracted in this case, doesn't matter. And I reach this equation here. So 0 minus 0 is equal to 0. And that is, 0 is the biggest number of all these calculated values that I have. So here's -2, here's -2, and there's 0. If you think about it, -2 is smaller than 0 because of the negativity. So you put that 0 there, and then you add an arrow to say that this 0 was calculated from the diagonal calculation. Now, I know there's a lot of things going on here, and I'm not going to ask you in a test or whatever it is to recite this algorithm like this, because when I first saw this, I had something of an allergic reaction to it. But I do think it's important, though, just so that you know how this thing is working, to see how the algorithm can come together. Because this algorithm, there are many variations of this kind of algorithm in computer science. I think that it's just cool to know. So let's move on to the next one. So here we have T and T. Again, you can see the red T's. So T and T are the same. They are a match. So let's go back and see what we have to do. We have, for instance, from right above where I am, I have -2. So I'm going to put my -2 here. From right next to me on my left, I have a 0. So I'll put my 0 right here. And then what I'm going to do is I'm going to think, okay, well, let's do my gap scores. -1, -1. These are all scores from the gap. And then I calculate my upper box value, which is going to be equal to the -3, and my side box, which is going to be equal to my -1. Then I have to handle my diagonal. And so diagonal, what I do is I grab this -1 here, which is this value there. And because t and t are the same, because they match, I'm going to award myself a point, which is 1. So I award that point to this guy, the diagonal score. So that's -1 plus 1, or 0. And then I say, okay, well, 0 appears to be the biggest value that I have. Isn't that terrible? If you're a 0 and you're the biggest value that, that exists in all the numbers, man, 0 must have some pretty strong self-esteem to be able to keep going like it does. But still, you have this 0 that shows up, and that's where that comes from. Then I put an arrow to say that my 0 actually came from the diagonal calculation. Let's move on to another one here. So here again, I'm going to look above me. This is how I do this. I say, okay, here's my above value, which is -3. Here's my side value, which is a 0. Just put those values in like that. And I say, okay, what was my gap value? Oh yes, my gap value, my gap penalty, I guess I should call it, is a -1. So then I put the -1 here, and I put the -1 here next to these values that I just collected from my the -3 and the 0. And then I figure out the values for my upper box, or the cell right above me, and that's -4. The side box is 0, this 0, -1, and that -1 is, remember, the gap. Just remember the arrows here. You're going left or you're going up. That's where you use this gap. You never use that for the diagonal. The diagonal is used for this one over here. So I have these calculations of -4 for the box right above me, and for the side box, I have a calculation of -1. And then my diagonal, where is that going to come from? I grab this value here of -2, and I say, okay, well, t does not equal c. And by the way, this is the only time where it really matters whether the bases are the same or not. And I hate to say that, but it's the only time that it really matters, is when you're calculating the diagonal. Otherwise, you don't care about that when you're working with this value and this value to calculate that value. So the diagonal says -2, and so what am I doing to it? Am I subtracting or awarding points? So what am I doing? Well, because this is a mismatch, in this case, the mismatch is 0. So I don't award myself any points, but I don't take any points away. And so your diagonal is going to be that -2, which I'm taking from here. And then I add the penalty score of 0, which is right here, and I still get -2. So then I have to go through each of these values and say, okay, the first one is -4. The second value that I have is -1. And the second, or after that, I have my other value is -2. And I think that -2 and -4 are they're bigger negative numbers. And so the max number is -1, which is why I have this value here. It is tricky if it's late and you're working with these things and you see like negative values. Please stop and actually take note of the negativity of these values, because you might look at it and say, oh, 4, that's bigger. But actually, it's -4, and that's smaller. And so please take note of those. Okay, I have done, for these slides, I've done the whole square, basically. We can keep on going. I think that you could, there's a bunch of, yeah, we can, I think you'll get the idea after the next row here. So then let's do this again. So here we have T and G. T and G are not the same. It's a mismatch. But what I'm going to do, first of all, to start this out, is I'll go to the square right above where I am, or the entry where I am just above, and I'll take that -4 and put it right down there. And then I'm going to go to my left. I'm going to take this -1, and I'm going to put that right there. And then I've got to figure out, okay, what am I doing here? This is the gap, -1. So I say, okay, so -4 minus 1, that's equal to -5. Then I have -1 minus 1, which is, I'm working with this -1 there, which I put right there. And then I take this -1 from my gap, and I put it right here in my equation. So I have -1 minus 1 is equal to -2. Okay, fine. And now I need to know whether these things mismatch or not. So then I go to the diagonal, and I say, okay, -3. I'll just go ahead and put that down here, and I'm going to check to see, well, what is it? T and G, they're not the same. So it's a mismatch, and so I'm going to be giving myself a penalty of 0. So I take this value that I got diagonally, -3, and I'm going to just subtract that 0. Yes, sir?
Not that this really matters, but why would the arrows be counter to the direction we're calculating.
Okay, so the question is, what is the significance of the arrows? I have a slide in that like toward the end of this that shows you what these arrows are about. But the arrows are there to remind you about how you got to that cell. How did you get this number here? So, for instance, here -2, you need some kind of system here to remind you that the -2, this value was awarded not from a calculation with -4, not from a calculation with -3, but rather the calculation with -1.
Well, wouldn't you like, again, it doesn't change the math at all, but wouldn't you just like go have the arrow come from -1 to -2? Like that's like where would you?
Oh, I see. So again, the question is, couldn't we just follow the numbers themselves without the arrows? Well, you'll find that the numbers are not necessarily telling of how the best alignment. It's not always the same. So you'll find that the numbers are misleading. So you really do need those arrows though, because the arrows will show you kind of like where the matches are and where the mismatches are. And in fact, well, I can show you something after this. After we finish this, there's a that we're going to spend some time looking at, and you can see from the arrows that they put up, you can kind of get an idea that that's how you figure out how this aligns with this. Like, remember, like, for instance, when we were working with the BioPython on Wednesday, when we did all those, we actually printed out those alignments to the screen, where you see like how one sequence is aligning with another one, and you can see the gaps and things. The arrows inform where those gaps are. Like, that's how you know where the gaps are. Otherwise, the numbers themselves will just get higher and higher, and you have to follow those. But you also need to know kind of like where you're supposed to go from that number next. Because the thing is, I mean, this isn't a very big example, but you'll notice that there are some times where it looks like it would be logical to go from, I don't know, -1 to -2. You know, that looks like a perfectly good solution here. But the thing is, though, that you have to go by the actual the algorithm or the calculation, which is this, and so you have to know like which pairs of numbers were they that were actually put into this algorithm to determine the likeliness between two different bases. So hold that question for a second. It's a very good question. And when I first saw this, I thought, what are these arrows doing here? I'm just getting confused. Hold that question for just a moment here, and I think that hopefully by the end of this slide deck here, you'll have your answer. Okay. So anyway, but you do have to put the arrows down there, because the arrows will give you this overall kind of view. The thing is that every cell or every entry here is going to have its own arrows to worry about. So let's do the next one here. So we have C is not equal to A. C and A are different. And so what does that mean about about these things here? Well, they're a mismatch. So again, what I'm going to do is I'll just start my calculation, and I'll just put a 0 right here for my upper box. I'm going to start my other calculation here, and I'll put this -2 right here for my side box. If you write your numbers out like this in some very straightforward, very basic way, and you approach your calculations in the same way each time, then it's less work it's less work in the end, because you're less likely to make a mistake. And because if you make a mistake, for instance, then every calculation after that mistake is wrong. So it's like they pile up. And so, for instance, if my 0, if I put that down as like -1, for instance, when it's supposed to be 0, then every calculation that depends on that 0 is going to be wrong. It's going to be off by 1, and that's actually going to give you the wrong the wrong alignment. So you want to make sure that you don't make any mistakes if you're doing this by hand, because it's going to be just a real mess to try and undo. Okay, so let's see. So I'm going to start my calculation by put my 0 up here. I'm going to put my other -2 right here for my side box. And then I have to go, okay, well, my gap is -1, so I'll put my -1 here. For the upper box, I'm going to put my -1 for my side box right here, and then I'm going to actually do the math. So 0 minus 1 is equal to -1. The side box is -2 minus 1 is equal to -3. And then I have to worry about my diagonal. So the diagonal is this -1 right here. -1, I'll put that value right here. And because C and A are mismatches, I have to give myself a penalty of 0. And so -1 plus 0 is equal to -1. Now, here's where things get kind of crazy, and that is that you get two maximum values out of this thing here. You have -1, -3, and then an additional -1. And so what this means now is that you have two different arrows to put. So every time you find a max value, that's really an arrow that you have to put down here. So your one arrow is going to be from the diagonal, which is right here. That's this arrow that goes from this -1 to this -1. And then I have my upper box, or the cell directly above where I am. That's this 0 and this -1, and that's why this arrow exists there. So getting back to your question, hopefully this makes some sense, is that the numbers have to have those arrows because you may have multiple routes right back from to align one thing to the other, but you have to know kind of like what exactly was the algorithm's alignment, I guess highest scoring alignment. Okay, I hope that you're not getting tired of this. I find this stuff actually kind of riveting, but they say that if you look at Isaac Newton's papers, he was a guy who was absolutely passionate about just calculating things ad absurdum. So he just he'd calculate random numbers and or irrational numbers and just keep on calculating things out and further and further and further and further just because he loved it. And so I hope you don't think that I'm that same person too. I think that's kind of a strange way of doing math, but this is, you feel like you're doing the same thing every time you're working on a square. It's like you're working with all these numbers, and it's like you're doing this all day, and your actual alignment isn't that complicated. But let's do the next one here. So again, I'm going to do I'm going to check to see whether C and A are the same. They're not the same. That's a mismatch. So I'll grab my 0 right from above me. I'll put that over here in this equation. I'm going to grab my -1, which is right next to me, and I'll put this in this equation for the side box. And I can even put my diagonal line here, if you want, my diagonal value right there. And then I think, okay, well, let's see. So if this is, my gap is -1, and that works for for the entry right above where I am. So I'm going to put this -1 here for the upper box, and I could have another -1 here for the side box. And then I'll do the equation. And so that's -1 for the upper box. For my side box, or the entry right to or that's to the left of where I am, that's -1 -1, so that's -2. And then I have my diagonal, which is this 0, which I've taken from here. And because C is not equal to A, that's a mismatch. And so again, that's a penalty of 0. So 0 plus 0 is equal to 0. And again, this is my maximum value. And because this is my max value here, from the diagonal, that's an arrow between the 0 and the 0. It keeps on going, you guys. No, I don't mean to take up all your time with all this stuff here, but this is like the last calculation, and then the rest of them I fill them in all for you so that you don't have to keep being exposed to this. I know that some people are thinking like, enough, I get it, okay. Okay, the next one is the top box over here, which is -1, putting that over here. Whoops, over there, and then I'm going to take the side number over here, which is 0, put that over there. And now, because these are my directly above and directly to my left, I have to worry about calculating the gap. So I'll take these numbers I've just taken away, -1, -1. Now do the math. So -1, -1, that's equal to -2. 0 -1, that's equal to -1. Now, for my diagonal, I put my 0 down here, and I check to see whether the bases are actually the same, if there's a match or whatever. Actually, this is not a mismatch. I made a mistake there. That should be a match. But we have C is equal to C, and so that is a match. Actually, that's a typo. I'll fix that. I'll fix that when next you get these slides. You'll find this typo fixed. But you'll find that there's a match, and so what I'm doing now is I take this diagonal number 0, put that down here, and then I add 1 to it, and the 1 is going to come out of this value here, match. That's my max value. And so then, because that's my max value, I have to put my arrow between the 0 and the 1 right here. So there's that. And the last one that we'll do, and then I'll fill in the rest of the row for you, and you can work this out as an exercise left to the reader if you'd like, but you'll have the answer so you can work it. I'll leave those undone. You can put those calculations in yourself if you'd like. Next one is okay, so now we have, again, I'm right here, I'm looking at the yellow, or the red rather. so I'm going to take my -2, take that down from my upper box. I have my 1, put that down over here for my side box. And then I look at my gap, -1, so that's where this value comes from here, -1. That's where this value comes from here too, because that's -1. I do the math, -2 minus 1 is equal to -3. 1 minus 1 is equal to 0. And then the diagonal, which is this -1, which is where this value is going to be coming from. Now, the diagonal, I need to know if they're a match or if it's a mismatch. This is actually a mismatch. So that's a penalty involved of 0. And so that's -1 minus 0, which is equal to -1. Then I go back and I look at all the values. Here's -3, here's -3 here, here's 0, and here is -1. It appears that 0 is the, it appears that 0 is the max value. And so what that suggests to me now is that this value is 0. And because because the max value was actually taken from the side value right here, I have to put an arrow to say how that number became. So you're going to use these arrows to work backwards. So when you do the rest of these calculations, and I do invite you to try them. Did you have a question, sir?
Yeah. So the sides are picked by like the sequences you're comparing, right?
Yes.
So how does this work? Like, how do you get a value for sequences of different sizes?
So if you're working with sequences of different sizes, then what you need to do is, like if over here is a 4 and down here is a 3, you put in, if you wanted to expand this thing out, you'd have to put in just a hyphen, if you will, like underneath this A. So the next row would just be hyphens, and they would all be mismatches. You know, they'd all be gaps. Or you'd still do the same thing, gaps or mismatches. But it's a very good question, though. What do you do, though? You'll see. We have an animation for that. We have an animation for that. Very cool. But do try doing these calculations. You have the answers here, and you can. And I think that you'll see how this works. But the reason why we're going through this, though, is because there are many other algorithms in bioinformatics and in computer science which function just like. Let's go back to this. Just like this, where you're supposed to pick a maximum value. If you look at this, this Fij, that's your function here. But your function is you're really picking the maximum value of maybe 3 or 4 calculations. In this case, you have 3 calculations. When you're working with the Smith-Waterman algorithm, which is the local alignment, you have a 0 that's also in this algorithm. And so you're comparing the numbers that you've calculated by this means that we've just seen here, and then you also have like a 0 thrown in there too. And so if 0 is the biggest thing, then you add 0. I'm not going to worry about that one, but it's the same algorithm. It's just that there's a 0 now that I have to add in there. If a 0 is my maximum value, then I have to include that there. So anyway, but the thing is though that at the very end of this whole thing, getting back to the question about the arrows, how do I actually use these arrows? Well, what I'm going to do now is I start at this value here, 1. Let's go back here, and I'm trying to jump. I have from 1 here. I have arrows, and so think of this as like remember the game that we all played when we were little, like the floor is lava. I still play that game. You should see my office. but what I'm saying though is like the floor is now lava here, and you can only step in places where there's an arrow. Otherwise, you'll burn your feet. So that means that the floor is lava here, you cannot go there. The floor is lava here, you cannot go there. And so here, if the floor is lava, the only place you can go is by taking a bridge, which is an arrow. So now you start at the biggest value, and you work your way back, following only the bridges, because remember, the floor is lava. And so what I'm doing now is you start, when you just figure out the arrows that you can actually take, because everything else will burn your feet, you start here, and you can go there, because this is an arrow that takes you there. And you can't go up. You can't go above to the -1. You can't go to the left because there's no arrow to the 0. Instead, the only thing you can do, because the floor is lava, is go to the 0. And so what you do is you're following these arrows back. And then while you follow these arrows back, you're creating your alignment starting from the right-hand side, working your way back to the left. And so here, I'm going to say that G aligns with an A. And so I put my G up here, and I put my A right there. And then I take my arrow, which is diagonal, and so that means that now I'm putting a C right here, And because I have, I have this one over here, I have this one right here, that means I can put a C right above it, or sorry, below it. And then you kind of get the idea that how you can work with your diagonals. And then over here, the next place I can go from this arrow is this value here. So I put a T up here. Hopefully you can see where I am. And then there's another T on the other side over here for the alignment itself, and that's where this T is going to come from. But now I'm up here, and there's an A, because this is the only place this is the only place I could have gone because of the arrow and the floor is lava. So I put an A above here, but if I look at the column over here, all I have is that gap. So that's where this gap here comes from. So the question is then, if I have longer sequences where, for instance, there's like, supposing this sequence up here goes on for 4 or 5 more characters, and this one remains just at 3 characters, what can I do? How do I put that into my Latin square here? What you're going to do is you just put gaps just like this, and then you run the calculations as normal, and you're just really looking to see whether is A the same thing as a gap? No, it isn't. So therefore, it's going to be a mismatch. And so you run the same calculations as we've seen here, and you'll find that everything works out like that. But the thing is, though, that once you have these arrows, and you pretend that the floor is lava, and you can only go from one square to another, one entry to another entry, for which there's an arrow that bridges them. Then if you follow those arrows back, then you'll find these are alignments you get. So let me just take you through and show you this for a second here. This is actually a very useful tool. It's purely educational, I would say. You probably wouldn't use this for your science, but maybe you would, I don't know. But what this is though, you can put in your own sequences. You can all see this. You can put in your own sequences, and then you can kind of, as you run your mouse over these things, and just go ahead and try it. You can see the arrows, but you can see the 3 calculations which have to be done. But you also have, in the lower right-hand side, you have something called the winning maximum score, which is basically the score, which is the max value. Go ahead and, I'll give you like just a couple minutes here. Just go ahead and just look at the numbers here. Just like put in, let's see, let's put the sequences that we're just working with. How about that? Whoops, not that one yet. Let's go ahead and put the sequence in. So the sequence was ATCG. I don't know why I have to read that in such. ATCG. That was the first one. What was the other one? TCA. TCA. It's this. And so this should be the correct score. So let's see. Did I get this right? Am I putting the right numbers in? Oh, you know what? I have to change my gap scores. So I have these scores like right here. Now remember that when I did this here, the gap that I chose was just -1. You can change the scores as you like. The application is you would change the gap scores because you might have, for instance, you want to exhaust. I don't know. You want bigger values maybe for your algorithm for longer or for shorter sequences, and maybe you want smaller values for the algorithm if you're working with longer sequences. You may have different applications. So you can change those values. And so I'm going to put this gap score now as a -1. Then I have the match score as a 1. So I go over to, okay, so match score is correct. The mismatch, though, is incorrect here, so I need to make this as a 0. And I think that this should be the same. So let's see, 0, 0, -1, -2. 0, 0, -1, -2. Okay, that's the first line is correct. Let's see, the C row is -1, 0, 1, 0. -1, 0, 1, 0, so these are correct. And the next one here, I see on the bottom, is -1, -1, 0, 1. And here we have -1, -1, 0, 1. So we got it, yay! Sweet. Go ahead and give it a whirl, and just try this out, and just kind of like look at the values. I'm going to find something, and I'll be back with you in a second here. I think that there's something else that I wanted to show you, which I don't think I put online, which I'm going to put into your class docs repository in a second here. But go ahead and just spend a moment just looking at that and just seeing how that works. And I think you'll find it's actually quite cool. Let me just, I'm actually finding a spreadsheet that is that allows you to you can see how the calculations work by using a spreadsheet, which I think is actually kind of a cool toy that you can play with. I'm also fixing something. Let's save that. All right, so what's the value of this one? Oh, that's, there we are. Okay, so hopefully everyone has had a moment here. I'm going to give you just another 30 seconds or whatever. I'm going to send out some more things to the class docs repository, and I think that I should have put these out last night, but I didn't. Okay, so then if you pull over your class docs repository, you'll have this new thing that I've just sent out now, which I think you might find quite interesting. See what it looks like. I have to actually bring this up on my screen so that you can see this. Give me a moment. Where is that? Okay. I'm just looking to get this thing up there, but it should be up there very soon. There we go. And I have to change the size, and I can show you. Okay, so if you pull over the latest repository, I've just now sent over some new things for you. I think you'll find that there's a spreadsheet in there called Global Local Alignment Demo, which looks like this. I'm not sure why the other slide reset itself, but it looks like this. And so what this is actually your global local demo. And by the way, I've just fixed the I fixed the slides here, so you'll find that where the mismatch, I changed this from match to match. That's good. So you have this, and so now what you can let's go back to this again. So we can recreate this same kind of square in a spreadsheet. And so let me just show you what that looks like. And so if I go down to, how do I get back to my, you know what? Sorry. There we go. I just can't find my things here. Get my bearings right. So you can go ahead and change these things here. So you'll see that in these squares here, I hope you can see them. Each of these squares, you have, for instance, the equation, which is exactly the equation of the algorithm. In other words, for instance, you can go to here, and if I look at, I have so many things on my screen. It's just hard to. I actually have this algorithm keyed in to the spreadsheet, which is actually kind of interesting. I mean, you can do that. And so you have this, so you can play with the algorithm if you want. But what this is doing though is, like, for instance, I can change this C to a G, and as I'm doing, what I want to show you though is that you're actually changing all the other calculations that follow from that calculation are all changed. So I can put like T. So you can see that the numbers are all changing. So let me go ahead and just like put the same number values down, or the same sequence value. So I have C, G, C, A, T, G, oops, A, G, and then another T. That's probably it. But you can see though that when you change the values up here, the values going down, or when you change the bases, or if you change as you're changing these bases here, the equations, or the calculations, I should say, moving from that point on, all of those numbers will change. So for instance, if this is now a C, you'll see that all these numbers down here have all changed. And that is one of the problems with working with this algorithm, and that is that while these numbers will change if the bases are different, if you make a mistake in your calculations anywhere here, then all the forward are all they're all going to be wrong. And so that's why you have to be very, very careful when you're putting together your, like when you're actually calculating your things out, you calculate them in a kind of a system like this. And this is the system that I use, but the system that you choose to use is entirely up to you. And you can do whatever you can use whatever system you'd like. But you have this interesting tool to look at, though, to kind of give you an idea about how you can use this. Now, so this over here is the global alignment. But one thing I wanted to say, though, is that local alignment is a little bit different, and that is that instead of, if you look at the original equation, which is all this stuff over here, just finding the max value of this calculation, with alignment, you also throw in a 0 in your equation. And that 0 then says, well, you find the max value between the 3 calculations that you do, and then also you have to compare that max calculation to a 0. 0 is the maximum calculation, or sorry, the maximum value that you've calculated, or that you have in your equation, down. And what that does, exactly the same. But what that does, though, is it makes these neat little pockets of areas, which actually look like this whole square here. All these numbers here, but actually those squares are all kind of tucked away as a subsection inside the sequences themselves. And so what this means, though, is that you're now able to look at the local alignment, which says take this sequence and then look at the chunks inside the sequence to see whether any of those chunks inside that sequence are the same as any chunks that I may find in the sequence. So now I can see actually that from here, it looks like these 4 T's together and these 4 T's on the side here, those T's are actually, oops, I've just done something wrong here. I won't do that again. But what I'm saying is that that chunk of code there is the same. It's embedded. The sequence works. You have a bunch of C's up here at the top, and over here on the side you have a bunch of G's. But the only thing that's actually common to both of these sequences are the T's, and you can see where those T's are by the numbers. And so what you would do is you'd say, okay, well, here's my maximum value, this 4. And so what I'm going to do now is I'm going to say, well, 4, and then you'd have to, obviously when you fill out the algorithm, you'd have your arrows. But then you're jumping to the other squares that you can go to, the other fields you can go to, because the floor is lava. But you're using those arrows as bridges to get you there. And then once you figure out how you got there, that will give you the local, how this chunk of code over here in this piece of DNA, or this protein, aligned with the chunk of code in this piece of DNA, or this sequence. It's very cool. And the funny thing is, though, that when this came out, though, I mean, we look at it now and we're thinking, that's kind of a simple idea. But when this came out, though, this was really a kind of a revolutionary idea, because one of the big problems was sequences. How do you do that? How do I compare sequences so that I can see kind of like where the alignments are, and I have a nice coding system, something to guide me perhaps as I try and piece together where these pieces, how these sequences come together. This dynamic programming solved that problem. This is where you would set the scores and the matches. You always need these scores here somehow. And I think over here, yep, you have the same things here. This is actually where the scores will come from. So I can change this match, not just 1, but give it like 1,000. You can see that that's a bit too much, but you can see that it does change the values. Anyway, so you can play with this and kind of like see how you can use spreadsheets in new and cool ways, if you care about spreadsheets. I had when I did my math degree, I had a teacher who was absolutely passionate about Microsoft Excel, and every single class he showed us some new Microsoft Excel trick. He's like, forgive me, I just have to scratch this itch. Let me just show you this. And like, okay, fine, whatever. So this is my salute to him. Are there any questions over this thing? Let me go back to the slides here. You have 2 different ways of doing this. You have this tool here, which is online, which gives you some pretty good education, I guess, or some good ideas about where these numbers came from and how to calculate the numbers. This one here. You can actually move your mouse around and you can see where the calculation came from. This is actually a very good tool. And you have that, and then you have this ridiculous spreadsheet that I've just given you. So you have some ways of actually kind of like you should be able to like make a square like this and to correct it and make sure that it is actually correct. Anyway, so getting to the alignment here, this is getting back to your question before, where we're talking about like how do I get back from how do I actually figure out what the alignment is? Well, you're using the arrows, and the arrows in this case here, again, if you imagine that the floor is lava, you can only go from one square to another square, provided that there is a bridge or provided that there is an arrow. And so here, I'm looking at the best score, and that tells me, or the highest number in the lower right corner, and that tells me where I can start. But it doesn't tell me where the next step is or the next square that I can go to. It doesn't tell me where that is. The arrows tell me where that is. And so looking at this kind of an arrow arrangement allows me to kind of get back to the beginning and to figure out what my alignment's supposed to look like, which is just basically underneath where I am now. This alignment on the right-hand side is how the gaps will all work out. Notice, though, that as you're moving, if you're starting, I can't really point to anything here, which is a shame, but as you're starting at the 0 and you move to the left, you have that 1, and when you're going diagonal, and if you're taking diagonal arrows, then it's basically a 1-for-1 type of alignment. But when you're jumping either to the left or you're jumping up from where you are, like if you're following an arrow that's going directly left of you, or you're following an arrow that goes directly above you, then that's indicative of a gap. And that's where you're going to have these gaps coming from that looks like, you know, these places here. That's a gap, this thing. Okay, so let's just see how these arrows work for this particular example. And by the way, you can check this over here, this example. Every time you're working on these things, though, every time you want to like work this thing out using this code or this online software here, you need to fill in these matches in that code. And that's how you're going. And you also need to fill in those matches. If you're using the spreadsheet, then you have to use the gaps, matches, scores over here. All right. So what does that look like here? So what I'm doing is I'm going to start at the 0. There's no there's no arrows here, but I'm going to assume that this line here knows where the arrows are. So basically, this is what the direction would be that you're taking to get back to your original starting point. And so this is your path. But you know which path you're supposed to go based upon the notion that there are arrows. Here's another one here. I mean, you don't have the arrows again, so it's kind of difficult to see. But notice, though, that when you are when you're taking side steps, that really indicates that you're going through some gaps. So, for instance, here, if I'm starting at the very, very bottom here, and hopefully you can see what I'm pointing at the bottom here, the bottom right, because I'm taking a step to the left, that suggests that I'm going. Actually, there's a gap that I'm making, and because over here I'm making 2 steps to the left, there are 2 gaps. I feel like I'm some kind of dance instructor. 2 steps to the left, 2 steps to the front. Take a sideward or a diagonal step. Anyway, but you get the idea. But what I'm trying to say, though, is that this is the same. It should be the same sequence. It's the same sequence that has different alignments. Now, we saw this when we worked with BioPython, where, remember when we looked at the alignments, we saw that there are many different ways that things could be aligned. Now, all of those, provided that the score is the highest score, they're all, I guess, what you call optimal. They're all perfectly viable solutions. And you, as the bioinformatician, have to look at these results and determine, using your education, which is the most likely. Which is the most likely to happen. So I have 3 different. Here's it. I have 3 different eventual alignments that I could use. I have the one that's this bright pink. I have this one that's purple, and I have this one that's dark green. I have 3 different alignments, and so these are all according to the algorithm. But remember, the algorithm doesn't have the smarts that you have, and so you have to look at these and say, well, you know what? I'm thinking that maybe the pink one is a better predictor of commonality. And then someone might ask you why that would be. And you say, well, I'm saying that because this one has this C, which is 2 gaps away from the GCA, and this one over here has this A, which is 2 gaps away from this CGC. And so while it's still a good score and it's still a perfectly fine alignment, it just seems that it's a little bit random here. So this could have been just a randomly placed C. Whereas this, I have 4 pieces of the code which were actually together, back to back, that perhaps this was the way that it was, and then I had a whole bunch of, maybe this was the original sequence, and then through a series of mutations and insertions, I have this C which was inserted, then an A was inserted, and then I had a T which was inserted, and at that point, this one organism became 2. And so you have to decide for yourself, and so that's one of the problems with algorithms. Remember, going back to this algorithm, wherever it is. Okay. You'll notice that this algorithm is primarily used for DNA. There are no smarts in here. It's just working with simple algebra. And it doesn't incorporate any historical data. There's no probability theory that's built into this thing. It's just numbers. And so you have to actually kind of look at the results that are turned out by this algorithm and figure out, which alignment is it which makes the most sense in terms of this, which makes the most sense. Now, when we move into working with proteins, I think I might stop there. I think that's all we have time for. But when we work with proteins, the alignments that we have here are actually smart. What that means is that somebody has figured out the probabilities for particular species of finding a particular arrangement of protein amino acids being found together. If you find an arrangement where you have these 3 or these 4 together, that is a much higher score, because it's been seen before in nature, than when you just have 3 of these things hanging out together, like here and here. So when you have 4 together, that counts for something. And so when you look at aligning proteins, and we'll do that, it's coming up, I'm not sure exactly when that would, but it's coming up when we hit proteins. When we align proteins, you'll see that proteins, the algorithms that handle proteins are actually much more robust. And that's why we have computers to help us to work with those, because those algorithms actually have probability theory built into them based on something called the Bloxham, or the Bloxham table, which is the probabilities of actually finding 2 amino acids together in the same sequence or side by side like this. It's very exciting, and I get goosebumps every time I think about it. Anyway, I'm going to let it go from there. When we come back on Monday, we're going to hit part 2, where we're going to talk about this sequence alignment being used to work with an influenza outbreak, to actually figure out the outbreak itself. It's actually a very exciting area, because I think that when you read chapter 3 of the book, you suddenly kind of learn to appreciate, why is there all this effort spent in comparing sequences? Like, what do we care about this? What does it mean? And I think that this will explain a lot. Anyway, I'm going to let it go from there. Everybody have a great weekend, get some air, and we'll see each other on Monday. Take care, everybody.